Section 7.6 has us solving rational equations. Basically, we're going to have situations where we have an equal sign, we have fractions on either side, and our goal is going to be to get fractions out of the problem. So we're going to have to solve rational equations, solve for a specified variable in a problem. A rational equation is an equation that contains one or more rational expressions, and the term rational really means fraction in this sense. Rational equations have a variable and a denominator. Here's some examples. 2/3 equals 1/3x plus 3/x. 2/x plus 1/4 equals 5/2x. 11x over x minus 5 equals 6 plus 55 over x minus 5. So in order to solve equations like these, basically we're going to find all the values of the variable that make the equation true. If a variable makes the denominator 0, we can't really include it. Such a number would be rejected because division by 0 is undefined. So we're going to determine which numbers cannot be solutions of the equation. Multiply both sides by the LCD. That's the key step. Once we find the least common denominator, if we multiply everything in the problem by that least common denominator, we no longer are going to have fractions in the problem. So unlike before when we were adding or subtracting and we kept things over that same common denominator and it stayed a part of the problem, here when we're solving rational equations, we're going to still solve for the common denominator, but by multiplying all the terms by that common denominator, we're going to turn a problem that has multiple fractions in it to a problem with no fractions that we can solve. We're then going to solve the resulting equation and check the possible solutions in the original equation to make sure nothing's an extraneous solution. So if we started out with x over 6 plus 5/2 equals 1/3, we begin by trying to establish what the least common denominator is. So there's no restrictions on x because no value of x ever makes the denominator 0. All these denominators were numbers, there weren't x's in them, so I don't have to worry about that. What I do need to worry about is 6, 2, and 3 with the least common multiple between them. The answer is 6. If I multiply 2 by 3, I get to 6. If I multiply 3 by 2, I get to 6. So 6 is the least common denominator here. Remember that we're not going to change everything to be over 6. Instead, what we're going to do is we're going to multiply each and every term by 6. That way, something will reduce on bottom, taking a fraction out of the equation and leaving me with something I can solve that doesn't have fractions. So if I multiply by 6 on both sides, this 6 and this 6 will cancel and just give me x. This 6 and this 2 will reduce to a 3 and leave me with 3 times 5. This 6 and this 3 will reduce to a 2 and leave me with 2 times 1. Once I distribute the multiplication, you can see what happened here was these went away and left me with x. These became a 3. 3 times 5 gave me 15. These became a 2. 2 times 1 gave me 2. Now that I have no fractions in the equation, hopefully this looks real easy and I'm excited to solve it. I can say, well, that 15 doesn't belong over here with the x. If I subtract 15 from each side, that's how I wind up with the correct answer, which is that x equals -13. I could go back and check to make sure -13 doesn't make any denominator 0, but it doesn't because none of the denominators had x's in it. So my final answer would just be the answer -13. So it's important to note that if we multiply both sides of an equation by an expression that involves a variable, we have to check the apparent solutions to see if any of them are extraneous solutions. Here's problems that are only going to have one answer that I'm about to do on the whiteboard. And then I'm also going to do these problems that would have 2 answers out on the whiteboard. In each of these problems, our goal is to identify the common denominator and multiply the entire problem by it. That will effectively get rid of all the fractions and let me solve something that doesn't have fractions involved. So when I look at problem A, I see on bottom x, 4, and x. Really, the only numbers for coefficients I see is 4. These both have understood 1s. So I know that the greatest common factor is going to have 4 as its coefficient. I then look for the highest power of x that I see. I just see x to the first here and x to the first here. So I'm going to put 4x as my greatest common factor. What I'm really doing then is I'm taking this greatest common factor, 4x, and I'm multiplying it by each thing. First by 3 over x, then I'm multiplying 4x by 1 over 4, then I'm multiplying 4x by 8 over x. 4x times 3 over x, the x's go away and leave me with 4 times 3, which is 12. When I do 4x times 1/4, the 4's go away and they leave me with x times 1, which is just x. Finally, on the right hand side, when I do 4x times 8 over x, the x's go away, 4 times 8 gives me 32. If I then want to solve for x, I just have to subtract 12 here, subtract 12 here, and I'll get a final answer of x equals 20. That is the correct answer to this problem. I could plug it back in and say that 3 over 20 plus 1 over 4 equals 8 over 20, and I could show that that is mathematically correct. For now, what I'm going to do is move on to problem B. This problem I actually don't give you many like in the homework, I don't think, but basically this is just reinforcing the idea of cross multiplying. If I have one fraction equal to another fraction, the easiest way to solve this is take the bottom of this one times the top of this one. Take the bottom of this one times the top of this one. So this is definitely something that you'll be seeing in science classes when you're solving proportions and things like that. Basically on the left side now I have this top times this bottom, or 2 times x minus 1. On the right side I have this top times this bottom, or 5 times x minus 2. When I then multiply it out, 2 times x gives me 2x, 2 times negative 1 gives me negative 2. 5 times x gives me 5x, 5 times negative 2 gives me negative 10. I'm going to subtract 2x from each side to move this 2x to the right. I'm going to add 10 to each side to move this 10 over to here. These are equal and opposite, go away. These are equal and opposite, go away. Negative 2 plus 10 gives me 8. 5x minus 2x gives me 3x. If I then divide by what's in front of the x, I get x equals 8/3. I'd be fine with leaving it as 8/3. If you wanted to write it as a decimal, this would really give you 2 2/3 or 2.67. For part C, the best thing to do is to first factor anything that can be factored on bottom. I see this x squared minus 4. I can factor it to x plus 2, x minus 2. Once I've done that, I can see that the common denominator is going to be x plus 2, x minus 2. So I'm going to multiply the whole equation by x plus 2, x minus 2. What happens in the first fraction is the x minus 2's cancel, and I'm left with this x plus 2 times this numerator 4. In the second fraction, this x plus 2 cancels with this x minus 2, and I'm left with the 3 that's in the numerator times the x minus 2 that's left over. This is all equal to, when I multiply by this whole bottom, everything cancels, so I'm just left with the 16 that was already there. I now distribute out the 4 and the 3. 4 times x gives me 4x. 4 times 2 gives me 8. 3 times x gives me 3x. 3 times negative 2 gives me negative 6. When I combine my terms, 3x and 4x give me 7x. Positive 8 and negative 6 give me positive 2. I'm going to subtract 2 from each side. That gets me to 7x equals 14, which when divided by 7 gets me to my answer of x equals 2. Really, I would want to plug this back in to see if it works as a solution. If I put 2 back in here, 2 minus 2 would give me the 0 on the bottom of this fraction, and technically would be what's called an extraneous solution. If I have something that makes a denominator 0, it gets me into a fuzzy math thing where I can't really do what I just did. That's why it's called an extraneous solution, because it's not an actual solution to the problem. If I plug 2 in here, I'll get 16 over 0 here, I'll get 4 over 0 here, and really this won't add up and give me an equality. So even though x equals 2 is what I solved for here, it's not really an answer to the problem. I'll tell you, I didn't give you anything like that on homework, but I did want to make you aware that it's something that could occur in these problems. So in these types of problems, you could see an extraneous solution. In the ones that you've been assigned, I promise I'm not looking for you to identify extraneous solutions. When I go to do part D, really I need to see that I can pull a 5 out of this when I factor the bottom here. If I do that, I get 5 times 2x plus 1, because 10x divided by 5 is 2x, and 5 divided by 5 is 1. For that reason, I can multiply this whole thing by 5 times 2x plus 1. When I do it to the first term, everything on bottom cancels with everything on top, so I'm just left with 5x. For the second term, there's nothing on bottom to cancel, so this whole thing gets multiplied by that -4. -4 times 5 gives me -20, and then I still have that 2x plus 1. On the right-hand side, the 2x plus 1 and the 2x plus 1 go away, and they just leave me with this 5. 5 times 3x minus 1, to be exact. When I now distribute out, this 5x stays. -20 times 2x gives me -40x. -20 times 1 gives me -20. 5 times 3x gives me 15x. 5 times -1 gives me -5. 40x and 5x are like terms that combine to give me -35x, still minus 20, equals 15x minus 5. I'm now going to add 35x to both sides. Add 5 to both sides. These will go away, and these will go away as I intended. -20 and +5 gives me -15. Positive 15x and positive 35x gives me positive 50x. If I divide by what's in front of the x, I get -15 over 50. I can reduce that. 5 goes into both top and bottom. 5 goes into 15 -3 times. 5 goes into 50 10 times. So I wind up with a final answer of -3 over 10. If I were to plug this back in, the important thing is it does not make this or this 0, so it's not an extraneous solution. I could plug it in and solve back just to verify that yes, this does create an inequality, but I'm more concerned with, let me just make sure it doesn't make any denominator 0. The second group of example problems all has 2 answers, because it ends up being factoring problems where I set something equal to 0 and find more than one factor that could make the answer 0. Beginning with problem A, what I need to do is cross multiply top times bottom, So when I do this x times this 5 minus x, I get x times 5 minus x. When I do this 2 times this -7, I get -14. X times 5 gives me 5x. X times -x gives me -x squared. All still equal to -14. I'm going to take everything to this side and set it equal to 0 so that I have a positive x squared term. So I do plus x squared here, plus x squared here, minus 5x here, minus 5x here. On the left-hand side, these both go away and leave me with 0, which is what I was looking for. On the right-hand side, none of these are like terms, so they cannot be combined, but I want to write them in the proper order for factoring trinomials. X squared term first, then x term, then no power of x term. If I set up my parentheses here, x and x bring down the negative sign, opposite of a negative is a positive. I'm looking for 2 things that multiply to 14 and subtract to 5. Ways to multiply to 14 are 1 times 14, 2 times 7. 7 minus 2 is 5, so I put the larger one here, the smaller one here. So I now have an equation that says 0 equals x minus 7 times x plus 2. The question is, what could make this whole thing 0? Well, if I put a 7 in here, 7 minus 7 would give me 0. Even though this gave me 9, 0 times 9 would give me overall 0. So that tells me x equals 7 is one of my factors. If I put a -2 into this one, -2 plus 2 would give me 0. 0 times -9 also still gives me 0. So the correct values of x are x equals 7 and x equals -2. Again, if you're ever not sure what one of these factors, what would make it 0, just set it individually equal to 0. So for instance, set x plus 2 equal to 0. I can then do -2 minus 2 and find that x equals -2 is the correct answer. For part B, it's not quite as easy because I can't just cross multiply like I did there. I have 3 terms. What I can do is multiply everything by the common denominator. In this case, the common denominator is x minus 1 times x. So I'm going to write it as x times x minus 1 here. When I go to multiply the first term, these x minus 1s will cancel and just leave me with x times x. When I do the second term, the x's will cancel and it'll leave me with -2 times this whole factor x minus 1. This is equal to, the x minus 1s will cancel and leave me with x times 1, which is just x. In the next step, x times x would give me x squared. -2 times x would give me -2x. -2 times -1 would give me +2. And this is all still equal to x. I always want to make sure that the x squared is a positive x squared, so it's already a positive x squared and on the correct side. For that reason, anything that's on the other side, I want to move over to here so that I can set it equal to 0 to solve. So the only thing that's over here is a positive x. To get rid of it, I do minus x. These will go away. These are the like terms, so the x squared can stay. -2x minus an additional x gives me a total of -3x, still +2 equals 0. If I now go to factor this one, 2 parentheses, x and x, this negative sign goes here, this positive sign means the same as the first one, same as a negative is a negative. Now I'm looking for ways to multiply to 2 and add to 3. The only way to multiply to 2 is 2 times 1. This means that my x values that would make this 0 are either a 1 that would make this factor 0 or a 2 that would make this factor 0. So my final answer is x equals 1, 2. But there's one thing that we would really want to do, which is plug these back in to see if either is extraneous. I can see that 2 doesn't make any of the bottom 0, so 2 is a valid solution. Unfortunately, if I put 1 in, I'd get 1 minus 1 here, which would give me something divided by 0. I'd get 1 minus 1 here, which would give me something divided by 0. So really 1 is not a valid answer. It's an extraneous solution. When I go to do part C, I'm going to multiply by the entire common denominator, which is x times x plus 6. That means the x plus 6's cancel in the first term, and I'm left with x times x plus 1, which is what used to be on top. The x's cancel on the second term, and I'm left with 1 times x plus 6, or really just x plus 6. And on the right-hand side, the x plus 6's cancel, and I'm left with x times 2x plus 1. Next line down, x times x is x squared, x times 1 is x. Can just drop the parentheses here and say plus x plus 6. On this side, x times 2x gives me 2x squared, and x times 1 gives me plus x. Since this is a positive x squared and this is a positive 2x squared, if I subtract x squared from each side, I'll get positive 1x squared on the right. That tells me really everything needs to move to the right. So combining like terms over here, this positive x and this positive x, give me x squared plus 2x plus 6. 2x squared plus x is still on the right, but I'm going to subtract this x squared from both sides. Then I'm going to subtract 2x. Then I'm going to subtract 6. Over here, everything intentionally got rid of itself, so I'm just left with 0. On this side, 2x squared minus x squared leaves me with positive x squared. Positive x minus 2x leaves me with negative 1x, and the negative 6 doesn't have anything to combine with. I can then make 2 parentheses, put in my x and my x. This negative comes down here. That negative means different. Different from a negative is a positive. I'm looking for 2 things that multiply to 6 and subtract to 1. That's 3 and 2. So that tells me my x values. This would be 3 to make it 0. This would be -2 to make it 0. 3 and -2, if I were to put them in these denominators that we started with, they wouldn't make any of those 0. So neither of these are extraneous solutions. They're both valid solutions to this original equation. Section 7.7 applies these methods of solving rational equations to word problems. We're going to focus on a very specific type of word problem, which I call a work problem. In a work problem, we're going to have two people who can do the same task at different rates, and then we're going to ask them to work together and try and solve how long it would take to do the task if they work in tandem. So, basically, shared work problems is the core of what I want you to be able to do as far as a problem that involves rational equations, but is solvable with the techniques we have and applicable to the real world. So, we're going to use rational equations to model the shared work problems. We're going to assume the work's being performed at a constant rate by everybody who's doing it. An inlet pipe can fill an oil tank in 7 days. A second inlet pipe can fill the same tank in 9 days. If both these pipes are used, how long will it take to fill the tank? Always these problems give you a length of time that one entity can do something, a length of time that the second one can do something, and ask you what if they both work together. So here our time is being measured in days. The first pipe can fill in 7 days, the second pipe in 9 days. Where we want to begin is determining what each pipe can do in 1 day. So if the first pipe can fill in 7 days, in 1 day it does 1/7 of the tank. If the second pipe can do the tank in 9 days, in 1 day it does 1/9 of the tank. So we add together the 1/7 of a tank that the first pipe does plus the 1/9 of a tank that the second pipe does. That'll tell me what they can do in 1 day working together. Since the first pipe can fill the tank in 7 days, it does 1/7 of the job in 1 day. Since the second pipe can do it in 9 days, it does 1/9 of the job in 1 day. If we add those two together, we then get that it takes X days to both fill the tank, so together they can do 1x of the job in 1 day. That yields the equation where we're trying to solve for X, the number of days it takes for both of them to fill the tank if they're working together, by saying what the first pipe can do in a day, 1/7, plus what the second pipe can do in a day, 1/9, equals what they can do in 1 day together, 1/x, or what portion of the job. If we then solve for X, it tells me how many total days it will take them. So the equation becomes 1/7 plus 1/9 equals 1/x. We want to solve it using the methods in 7.6. Basically find the common denominator, multiply everything by that common denominator. Really, I don't even need to do the common denominator math. I can do that and I can make the problem somewhat easier, but really the easiest way to approach it is just to multiply by everything on bottom. When I say multiply by everything on bottom, I mean multiply by 7 times 9 times x. 7 times 9 times x is 63x. If I multiply the whole left side by 63x and the whole right side by 63x, I'll get rid of all the fractions. On the left side, 7 and 63x will cancel to give me 9x, plus 9 and 63x will cancel to give me 7x, and then on the right side, 63x and x will cancel to just give me 63. So I'm left with 9x plus 7x equals 63. Always on the left-hand side, you'll have like terms that can be combined. In this case, 9 plus 7, which gives me 16x. I then just need to divide by what's in front of the x to get my final answer. So 16x equals 63. If I divide by 16, that means that it takes them 63 over 16 days, or right around 925 or something like that. Basically, it's going to be just shy of 4 days. So both inlet pipes are used. It will take 63 over 16, or 3 and 15/16 days to fill the tank. first pipe fills 1/7 of the tank, the second pipe fills 1/9 of this much of the tank. When I add them both together, I get 9/16 plus 7/16 for a total of 16/16 or 1 full tank. So this is just checking that yes, it was the correct answer. You don't really need to do that check on these problems. You always can if you're not sure if you feel good about your answer or not, but it's not necessary to do the full check. I'm now going to do these 3 problems out on the whiteboard for you. And again, a majority of the problems, literally everything I asked on the test and homework, are these types of work problems as far as the word problems for 7.7. In these work problem examples, we always want to figure out, within the unit of time given, how much does one person complete in that unit of time. So in problem 1, they tell us one builder can build a house in 25 days. If it takes them 25 days to build a house in 1 unit of time or 1 day, they build 1/25 of the house. We're going to add to that a second builder who can build a house in 30 days. If they can build a house in 30 days, that means in 1 day's work, they've completed 1/30 of the house. Together in 1 day's work, they've completed X portion of the house, which means that if I solve for X, it'll tell me how many total days it takes them working together to build the house. You can look for least common multiples. You can do other things to find least common denominators. For these problems, what I almost always recommend is just brute force, multiply each of the 3 available denominators by each of the 3 terms. So essentially, I want to multiply by 25 times 30 times X. What that's going to do is when I multiply by the first term, the 25s will go away and leave me with 30 times X times 1, which will just give me 30X. For the 1/30, the 30s will reduce, and I'll just be left with 25 times X times 1, or plus 25X. On the right-hand side, the X will reduce and leave me with 25 times 30. Might want to use a calculator for that. If I put it in, 25 times 30 gives me 750. I can now combine 30X and 25X to get a total of 55X, which equals 750. If I divide by what's in front of the X, 55, then I get my answer of X equals 750 divided by 55, which is 13.64. No real reason that I go to 2 decimal places, just used to dollars and cents. It's a common thing to round to, but definitely be on the lookout for whatever they say in the instructions here. This would be 13.64 days that it takes in order for them to build the house working together. Each of these problems will work the same way. I'll want to identify in problem 2, if Dominic can fix a car in 6 hours, 1 unit of time is 1 hour, and he fixes 1/6 of the car in that time. We're going to add to that Amani, who can fix a car in 8 hours, so 1/8 of the car gets done. That all equals 1/x, where I'm trying to solve for x. Easiest way to do it is to multiply by 6 times 8 times x. First term, the 6's will go away and leave me with 8x. Second term, the 8's will go away and leave me with 6x. And on the right-hand side, the x's will go away and leave me with 6 times 8, or 48. 8x plus 6x gives me a total of 14x, which equals 48. I can then divide by that 14, and that would give me x equals 48 divided by 14, which is 3.43. So this would be 3.43 hours it would take Dominic and Amani working together to fix the car. Mr. Moulton can clean the house in 3 hours. That means he cleans 1/3 of the house in an hour. Mrs. Moulton can clean the house in 2 hours. That means she cleans 1/2 of the house in an hour. How long will it take them to clean the house if they're working together? Well, they finish 1/x in an hour. If we do what we've been doing, which is multiply the whole equation by each denominator, 3 times 2 times x. First time the 3's will cancel, I'll be left with 2 times x. Second time the 2's will be canceling, and I'm left with 3 times x. And on the right hand side, the x's cancel, and I'm left with 3 times 2, which equals 6. When I combine 2x and 3x, I get 5x, which is still equal to 6. I can then divide by 5, which will give me x equals 1.2. Or in other words, it would take 1.2 hours for Mr. and Mrs. Moulton to clean the house working together.